In this video, we're going to finish off chapter 6, which was on relations. In particular, I want to talk a little bit more about equivalence relations and partitions. Some of the stuff I talk about in this video might overlap with what I talked about in the last lecture. I'm recording this in advance, so I don't exactly know how far we will have gotten at this point. But if it does overlap, then this is a bit of a review. And then we will, in the next video, we'll move on to chapter 7. Okay, so let's talk a little bit more about equivalence relations and partitions. So first, let's just remember what it means for a relation to be an equivalence relation. So remember there was these three basic key properties to being an equivalence relation. The first of these key properties is reflexivity. So a relation is reflexive if every element of A is related to itself under the relation. I'm going to go through these fairly quickly, by the way, since these should be review from at least last lecture or the one before it. The second key condition is that it's symmetric. So a relation is symmetric if whenever x is related to y, then y is related to x. Okay, the way I'm writing it here is with a logical implication. So I'm writing that x, y being in the relation logically implies that y, x is in the relation. This is the same thing as saying that whenever x is related to y, you also have that y is related to x. The third property is transitivity. So this says that if x is related to y and y is related to z, then x is related to z. Oops, I've got this wrong on the slide. Let me correct that. So this should say x is related to z. Okay, so I've written this again like a logical implication. But you should read this as whenever x is related to y and y is related to z, you have x is related to z. So you can kind of skip the intermediate thing, y. Okay, and we recall that R is called an equivalence relation if it satisfies all three of these properties. So reflexive, symmetric, and transitive. So you should also remember we had another special property of relations, which was antisymmetric. Antisymmetric is an important property of a relation, but it's not something that shows up in the definition of an equivalence relation. So you should always remember equivalence relation is reflexive, symmetric, and transitive, not necessarily antisymmetric. And I suspect that in the last lecture, we will have also talked about equivalence classes. So just to remind you, given some element x in A, where A is a set and R is a relation on A, an equivalence relation on A, so and an equivalence relation R on A, the equivalence class of X is the set. So the notation is square brackets X, and this is the set of all Y in A, such that Y is related to x by the relation R. So hopefully you remember what this notation means, right? So I might switch between different notations as we go along, just so that you can get used to both of them. But y, r, x, remember this just means that y comma x is in the relation R. Okay, these two things mean exactly the same thing, so you should be used to both notations. And also to remind you what this means, so if you translate this into plain English, this means that y is related to x under R. So as an example, let's look at things related to chapter 5, so this modular arithmetic. So we could define an equivalence relation. So let, well, R be the relation on the natural numbers where x is related to y if x is congruent to y mod, let's say, 7. Okay, so we can ask ourselves, what are the different equivalence classes here? And, well, if you think about it, so if I take the equivalence class of the number 1, we get the set containing 1. So this should be all the, well, maybe I'll kind of explain it a bit slower. So this is all the y in the natural numbers such that y is related by R to the number 1. Or in other words, this is just the set of all natural numbers such that 1, or let's say, maybe I'll write it this way, so y is congruent to 1 modulo 7. Which of course is just the set of all numbers containing, 1, 8, what's next? I guess 15, 22, ... So it's the set of all numbers of the form 7k plus 1 such that k is a natural number. Actually, k is either a natural number or 0. So notice that if I was to write the equivalence class of the number, let's say the number 15, well, this is also the same set, right? It's the set of things which are related to 15 under this relation is exactly the same as the set of things that are related to 1, because to be related to 15, you have to be equivalent or congruent to 1 modulo 7. So actually, the equivalence class of 15 is the same as the equivalence class of 1, which is the same as the equivalence class of, for example, 29, because it's always going to be, the set 1, 8, 15, 22, and so on. Okay. If that's not clear to you, then please do think about what this definition, what this relation is saying, and then you can probably convince yourself that this is true. So the other equivalence classes here, so we have the equivalence class corresponding to the number 2, 3, 4, 5, 6, and 7. So these are all going to be different than the equivalence class. So these are all going to be distinct, basically. So if I take, the equivalence class corresponding to 2, that's going to be not equal to the equivalence class corresponding to 3. But if you think about it, these 7 equivalence classes are all the different equivalence classes. Because basically, if you take an integer and I look at the remainder modulo, or the remainder when I divide by 7, the remainder is either going to be 1 or 2 or 3 or 4 or 5 or 6 or 0. And this class is going to be the set of all things, with a remainder of 1. This is going to be remainder 2, 3, 4, 5, 6. And then you have to be a bit careful here. So this is going to be the set of all things with a remainder of 0. Okay. So if you think about it, this equivalence class has sort of broken up the natural numbers into like 7 different sets. And these 7 different sets are completely disjoint. So, there can't be any number which is in this equivalence class and also in this one at the same time. So these have no common elements. Okay. And this is only one example, but this is kind of part of a general phenomenon that happens with equivalence relations. So what happens is that you end up getting, your equivalence classes are going to break up the set on which the equivalence relation is defined into disjoint pieces. So this is connecting now to the idea of a partition of a set. So a partition of a set is defined as follows. So suppose I let A be a set, a partition of A is a collection, let's write it curly P, of subsets of A such that, so first of all, the empty set is not in P. The sets in P have to be disjoint. So if, let's say, Q and R are in P, and they're not the same set, so Q is not equal to R, then they have to be disjoint. Disjoint means that they have empty intersection. So maybe I've never used this word before, I'm not sure. But if I haven't, this word means, or the word disjoint. So 2 sets are disjoint if they have empty intersection. So meaning that they have to be, if I look at Q and R, their Venn diagram looks like this. There's no common points, no common elements. And the third property is that for every element of A, there exists an element in the partition, so in P, such that X is in Q. Okay, so the way you should think about this is kind of like this. You've got some set A, and a partition just means that you're going to break up the elements of A into separate kind of classes. So you've got one kind of class, which is, let's say, the things in the yellow set. you've got the green set. I'm not sure if this picture is helping or not. But basically you're kind of breaking up the sort of the elements of A into kind of classes. So then you've got the pink set, which might look like this. You've got the aqua set. I guess this color is called aqua according to PowerPoint. And let's say you've got an orange set. So basically the idea is, so these sets are all supposed to be disjoint. I know that in my picture I've sort of overlapped them, but there should be no overlap between the sets, and they have to cover all of A. And just to be clear here, so I've drawn the pink set kind of disconnected, but you should think of this and this as being together being one set. Okay, so the point is, a partition is a way of breaking up the set into disjoint classes. And just a bit more terminology. So the sets of the partition, well, we can call them lots of different things. I think in the notes it says that they are called maybe cells or blocks or just the sets of the partition. But some people also call these things partition classes. There's all different kinds of terminology here, but hopefully it'll be clear from context what we're talking about when we talk about the sets of a partition or the cells or whatever. Okay, so this, like I said, does connect to equivalence relations and equivalence classes. So kind of the thing I want you to take away from this is that basically, equivalence relations and partitions are basically the same thing. So what I mean by this is that if I have an equivalence relation, the equivalence classes form a partition. So the equivalence classes of an equivalence relation I should say the set of equivalence classes of an equivalence relation on A partition A. Well, I should maybe say is a partition of A. So let's kind of back up here. So the set of equivalence classes of an equivalence relation on A is a partition of A. And on the other hand, if you have a partition of A and you define two things to be equivalent if they're in the same cell, then that gives you an equivalence relation. So on the other hand, if P is a partition of A and we define R such that x is related to y if x and y are in the same cell of P, then this R that we get is an equivalence relation. Okay. And it's not hard to see this, right? Because think about the definition of an equivalence relation. So it will be the case that if two, it will be the case that the relation is reflexive because every element is in the same equivalence class as itself. It's also symmetric because if x is in the same equivalence class as y, then y is in the same class as x. It's transitive because if x is in the same class as y and y is in the same class as z, then x is in the same class as z. Okay. So, right, let's kind of prove a theorem which is going to explain this more formally. So this is called theorem 6.10.3. And it says the following. So suppose that that A is a set and R is an equivalence class, equivalence relation on A, then, well, for any x in A, x is in the equivalence class of x. Secondly, for any x and y such that x is related to y, we get that the equivalence class of x is equal to the equivalence class of y. And thirdly, we get that for any elements x and y in A such that x is not related to y. So I'll write that as xy is not in the relation R. The equivalence classes of x and y have to be disjoint. Okay. The punchline here, the main purpose of this theorem is that this means that the set of equivalence classes is a partition of A. Okay, so this is the thing that I want you to really take away from this. If I take an equivalence relation and I look at the equivalence classes, that gives me a partition of A. Okay, so let's prove this theorem. Okay, so let's start by proving the first bullet point. So I want to prove that for any x in A, x is in the equivalence class of x. Now, if it's not clear how to prove this, then I would say you really need to review the definitions of equivalence relations and really kind of get your hands dirty with this concept, because this first bullet point should be very easy for you to prove at this point. Okay, so this all comes down to understanding the definition of the equivalence class and understanding what reflexivity means. So for the first bullet point, recall that the equivalence class of X is equal to the set of all Y in A such that Y is related to X under the relation R. Now, since R is reflexive, we know that X is related to itself. So therefore, by definition of the equivalence class, X is in the equivalence class of X. Okay, so like I said, this all just comes down to understanding the definition of equivalence class, and understanding the definition of reflexive, and remembering that an equivalence relation is always reflexive. Okay. So now let's prove the second bullet point. So suppose that X is related to Y by R. So we want to show that the equivalence class of X is equal to the equivalence class of Y. And we should remember that these two things are sets, right? So the equivalence class of X is a set, and the equivalence class of Y is a set. So to show that the two sets are equal, what we can do is show that the equivalence class of X is a subset of the equivalence class of Y, and the equivalence class of Y is a subset of the equivalence class of X. Okay. Now to prove the first one of these statements, we have to pick an element of this set and show that it's in this set. Okay, this is really just reviewing all of your set theory proofs. So if you struggled with that part of the course, I think it's quite important to review it at this stage. So, okay, let Z be any element of the equivalence class of X. And we want to deduce that Z is in the equivalence class of Y. Well, so since Z is in the equivalence class of X, this means, apologies for the dogs barking in the background, that Z is related to X. And now so now what we know is that Z is related to X and X is related to Y. And now if we use transitivity, we can get that Z is related to Y. So by transitivity, of the relation R, we have that Z is related to Y. So therefore, Z is in the equivalence class of Y by definition. And so that proves that we have this subset relation. So the equivalence class of Z, or X, is a subset of the equivalence class of Y. So therefore, what we've proven is this. Okay. For the other direction, we can do the same proof, except what I want to do is use the symmetry property once to change this X related to Y related to X. So by symmetry, the symmetry property of R we have that y is related to x. Now, if we follow, so I'm going to sort of skip a step here. So following, I'll just say following the same argument as above, we can show that z being in the equivalence class of y logically implies that z is in the equivalence class of x. Okay, basically we want to do the same argument as above, except we want to use this instead of this. Okay, and when you do that, so this implies that, so therefore y is a subset, sorry, the equivalence class of y is a subset of the equivalence class of x. And now we've shown that one is a subset of the other in both directions, so therefore the equivalence class of x is equal to the equivalence class of y. Okay, so I would say that if it's not clear how to fill in those details, then again, you really need more practice with these definitions. So I'll kind of leave that to you to kind of think through the details of how can you apply the same argument as before to show this. And hopefully that's not too difficult. If it is, then like I said, it's really important to review these definitions. Okay, so we're not quite done here. We need to prove the third bullet point. So suppose that x is not related to y, and let's prove that their equivalence classes have, well, they have empty intersection. So in other words, this is saying that they're disjoint. Let's actually do the contrapositive. So for the third bullet point, we're going to use the contrapositive. So we show that if the equivalence class of x and the equivalence class of y have non-empty intersection, then that will logically imply that x is related to y. Okay, so in other words, I'm negating this statement and showing that it implies the negation of this statement, which is exactly how the contrapositive works, right? If we want to prove something implies something else, you can negate the conclusion and prove the negation of the premise. Okay, so if we're assuming this, what this means is that so if I have these things having a non-empty intersection, so if this is not the empty set, then there's a point, there's an element which is common to these two sets. So this implies that there exists a z such that z is in the intersection of these two sets. So in other words, z is in the equivalence class of x, and z is in the equivalence class of y. What it means for z to be in these equivalence classes is that z is related to x, and z is related to y. Okay? Now, by symmetry, of R, we can say that x is related to z, right? Because if z is related to x, which is what we wrote here, then x is related to z by symmetry. And now, by transitivity, we can combine these two statements that x is related to z and z is related to y to get that x is related to y. Okay, and this proves the contrapositive. Of course, the contrapositive is equivalent to the original statement, so we're done. Okay, so that completes the proof. Like I said, the thing to take away from this is that if I have an equivalence relation, I look at the equivalence classes, that partitions the set on which the equivalence relation is defined. Let's look at a few examples. So I realize now that I didn't give you any examples of partitions, so let's do a few. Okay, so suppose I've got a set A, which is, let's say, A, B, C, D, E. Okay, one equivalence, one partition. So the following are partitions of A. So if I take, let's say, the set containing the set A and the set B, C, D, E, so that's a partition. Or I could just take the set containing A, that's a partition, or the set A, B, C. So this, I should say the set containing A, the set containing B, the set containing C, the set containing D, and the set containing E. Right? And the point here is that in each of these three examples, every element of A appears in exactly one set of the partition. So the following, so if I, so here's some examples which are not partitions. Of A. So, for example, if I take A, B, C, D, E, A, this is not a partition because these two sets here are not disjoint. In other words, they have A is in both sets. And in a partition, your sets are supposed to be disjoint. Another non-partition is if I take, let's say, A, B, C, and just the set E. Okay, and the reason this is not a partition is because the element D does not appear. A third example is if I take the collection, let's say, containing the empty set and A, and the reason this is not a partition is because it contains the empty set. So a partition cannot contain the empty set. One more example, if I just take, let's say, A, B, C, D, E, technically this is not a partition because this is just a pair of sets, okay? To make this a partition, it's supposed to be a set of sets. So to make this a partition, I would have to put the set brackets around everything. So this would be a partition if I had the set brackets outside, but the way I wrote it before is not technically a partition, at least according to the definition we're using in this course. Okay. And like I said before, so what we've proven in the previous theorem is that if I have a partition, or sorry, if I have an equivalence relation, it defines a partition on the set that the equivalence relation is defined on. But in the other direction, if I have a partition of a set, you can get an equivalence relation by just saying two things are equivalent if they're in the same class of the partition. Okay, so I hope that was helpful, and I'll see you in the next video.